Diana joined the MPA in 2012 as Technical Advisor, Energy and Climate Change, and now holds the position of Director, Energy and Climate Change. Diana's responsibilities include environmental data collection analysis from UK cement plants, modelling the impact of EU and UK climate change and environmental policy on the UK cement industry, the UK emission trading schemes and renewable energy policies, managing industry's projects such as the MPA Decarbonisation Roadmap, modelling and production of the UK Cement Environment Production Declaration. Diana is the author of the UK Sector Sustainability Development Report and is responsible for administrating the climate change agreement for various mineral product sector. In 2019, Diana was part of the MPA team, which successfully applied for £300,000 from the UK government to undertake a feasibility study titled Options for Switching UK Cement Production Sites to Near Zero CO2 Emission Fuel. The success of this study led to a second successful application for 3.2 million of funding to demonstrate the use of hydrogen and biomass in the main burners of the cement plant at Ribblesdale and biomass and plasma energy in the Calciner and Tungsten cement works. The project is still ongoing. Prior to joining the MPA, Diana completed a PhD project sponsored by Hanson, an MPA cement member, at the time trading as Castle Cement, on sustainability lime mortar within the University of Bristol. This experimental PhD tested novel lime mortar preparations using various waste materials. Following completion of the PhD, Diana worked at the Environment Agency in the Evidence Directorate of the Information Scientist, which involves searching, analysing and presenting information on vitality and environmental topics. So we're very fortunate to have a good speaker today. So no further ado, I'll pass you over to Diana.
Oh, thank you very much, Steve. And thank you for inviting me along today to speak to you all. But I was invited along today to talk about the work MPA have been doing on fuel switching cement production to low or near zero carbon fuels. So I thought I'd start by giving a bit of a brief introduction to MPA, which may be unnecessary for you all, but it's generally a bad career move for me not to at least set that out. So I'll give a brief overview of UK cement producers and the production process before looking at some of the context around why we're doing these fuel switching projects. I'll also outline briefly the MPA Net Zero Roadmap, and then I'll move on to the meat of the presentation on the fuel switching work. So MPA is the trade association for the aggregate, asphalt, cement, concrete, dimension stone, lime, mortar and silica sand industries. We've got a growing membership of about 530 companies, which is made up of a vast majority of independent SME quarrying companies throughout the UK, as well as the 9 major international and global companies. We cover 100% of UK cement and lime production, 90% of GB aggregates production, 95% of asphalt and over 70% of ready-mix concrete and precast concrete production. In 2018, the industry supplied £16 billion worth of materials and services and was the largest supplier to the UK construction industry, which had an annual output valued at £172 billion. The industry production represents the largest material flow in the UK economy, and it's also one of the largest manufacturing sectors, which I'm sure you all already knew. So now moving on to a bit about cement, an introduction to cement. Of all the MPA product groups, it's cement that I'm going to be talking about today. So cement's produced at a number of kiln and grinding and blending sites across the UK. This map just shows the kiln sites because that's where the majority of the fuels are consumed and where the majority of carbon dioxide or CO2 emissions arise. Now, the majority of plants are remote from industrial clusters. We hear a lot about clusters in the news at the moment, and that poses challenges for some decarbonisation options. And 4 out of 5 UK cement producers are owned by large multinational companies with headquarters outside of the UK. And this just means that plants have to compete with sister plants all around the world for internal investment. It's also why I spend most of my time trying to ensure that policies and regulations in the UK don't add so much cost onto cement production here that those parent companies choose to shut down UK plants and replace domestic production with imports. Ideally, we want to ensure that we have a low carbon domestic supply of cement here. So this image here, which hopefully you can all see because I realise it's a little small, shows how cement is produced. So calcium carbonate and clay raw materials are heated to volcanic temperatures to produce an intermediate product known as clinker. This is then ground with other materials such as gypsum and secondary cementitious materials such as ground granulated blast furnace slag and fly ash to form cement. The key part for today is this part here. So the calciner and the kiln are where the majority of the fuels are consumed and where the majority of carbon dioxide emissions are produced. So in cement production, 30% of the emissions arise from the combustion of fuels, with the remaining 70% coming from the breakdown of the calcium carbonate or limestone raw materials. Now, you often hear that globally, the cement sector contributes 7% of emissions. However, at UK level, cement production contributes just 1.5% to emissions. I'm going to come on to kind of why that is in a bit. Now, traditionally, cement manufacturers relied on coal to reach the volcanic temperatures required. However, multi-million-pound investments have been made by UK manufacturers to switch away from coal. In 2020, 47% of the thermal input to UK kilns was provided by waste-derived fuels, and this totaled 600,000 tonnes of waste. So across the sector, we use around 14 different fuels now, and I've listed the main ones here. So we still do use a few fossil fuels, so coal, petcoke, gas oil, and natural gas. But then we've got some waste-derived fossil fuels in the form of waste solvents and plastics. And then we've got waste-derived 100% biomass and part biomass fuels. So tyres and refuse-derived fuel are kind of part biomass fuels. And then we've got sludges and wood and meat and bone meal. Well, that's quite a small proportion now, which is 100% biomass. Now, a key point on the use of fuels in cement manufacture is that the ash that remains once the fuels have been combusted forms part of the mineral content of cement. So in other words, it's recycled into the cement product and it doesn't form a waste residue that you have to dispose of after. So this makes cement co-processing, as we call it, distinct from other combustion processes like power generation, energy from waste, incineration and biomass boilers. And it's also important when we start looking at fuel switching because the mineral content of the fuels reduces the raw material requirement and changes the fuel mix can impact the quality of that clinker because the ash is remaining in the product. Each year, around 160,000 tonnes of fuel ash is recycled into cement. So that's a bit of background to MPA and cement manufacture. Now I'm going to move on to look a bit at decarbonisation ambition. So for some time, the UK has been a step ahead of other nations in terms of decarbonisation ambition. In 2008, the UK became the first country to legislate for a carbon reduction target through the Climate Change Act. The target set at the time was an 80% reduction by 2050 on 1990 levels. In 2013, MPA published a strategy setting out how the cement sector could meet that 80% ambition. Today, the UK's climate ambition is net zero, to be net zero by 2050. This is consistent with the temperature target set in the Paris Agreement to limit global warming to well below 2 degrees and preferably to 1.5 degrees Celsius compared to pre-industrial levels. To get the UK on the net zero trajectory, the Climate Change Committee advised that the UK greenhouse gas emissions reduction needs to be strengthened to 78% reduction by 2035 from the 1990 baseline. So in other words, they're saying that to get to to get to net zero by 2050, we need to be at least a 78% reduction by 2035. So at the national level, we know where we're heading. As we approach COP26, there will be further announcements enabling the net zero transition. This has already started with publication of the 10-point plan, the energy white paper, the industrial decarbonisation strategy, the Treasury net zero review, and we're kind of waiting on several others as well. So yeah, there's quite a lot going on. So as shown on the chart on the left-hand side of this slide, UK concrete and cement are decarbonising faster than the UK as a whole. Early action that's already been taken includes improvements in energy efficiency. So there's been a shift to the modern dry process kilns in cement manufacture, and away from the longer wet process kilns. There's also been quite a lot of investment in energy efficient plants and machinery. Fuel switching, I already mentioned, 47% of the energy demand in cement kilns is now from fuels other than the traditional coal. There's also been investments in product formulation. So the clinker content of concrete is less because the proportion of CEM1 in the market is now less, and because cementitious replacement in concrete has increased. So the use of that slag and ash that I mentioned earlier has started to increase. So the donut chart on the right-hand side shows that UK concrete and cement emissions are around 1.5% of the total UK emission. And I mentioned earlier that's about 5 times lower than the global cement industry contribution. And we've got a roadmap which kind of sets out now how that 1.5% becomes zero and how the sector could actually go beyond that to contribute to other sectors lowering their emissions. And this slide shows that roadmap. So it was launched by MPA in October last year, and it's titled the UK Concrete and Cement Industry Roadmap to Beyond Net Zero. It's available to download from our website if anyone's interested. Please do take a look. So this roadmap represents quite a significant milestone for the cement and concrete sector, as it clearly sets out how we can contribute and go beyond net zero by 2050. But kind of more importantly, almost, it sets out what is needed to get us there, not just from government, but also from the industry itself and from other stakeholders. So this waterfall chart is one of the key graphics in that roadmap, and it very simply shows the contribution of each of the different decarbonisation levers. So it shows this here is the 1990 emissions level, which is the baseline used by the United Nations and by the UK government. So when we talk about reductions, it's often done from 1990. We've then got a 2018 reference point, which is kind of like where we are today. You can see we've already made those significant reductions to get from 1990 to 2018. And then each of these bars represents what is possible through different decarbonisation levers. And these are expressed as a percentage of that 2018 emission. So you can see when we get down here, these two are sort of some of the downstream benefits of concrete in use. Start going below that net zero, which is the beyond net zero part of the title. So I guess the only thing here is it's quite important to recognise that this is just one possible route to get to net zero. And as some technologies develop, we might learn more about their potential contribution. And it might be that other things come along, or that, electricity becomes so expensive, for example, that electrification is completely out of the picture and, we do something different. But this is sort of one credible route to show we can get there. So one of the 7 decarbonisation levers set out in that roadmap is fuel switching. So as I've mentioned, a considerable amount of fuel switching has already been achieved by UK cement producers, and the net zero model kind of looks to build on this. So it assumes that by 2050, around 70% of the thermal input for cement production is provided by waste biomass fuels, and the remainder of the thermal input is assumed to be sourced from fossil fuels still. There is a potential for us to be even more ambitious than this on the fuel switching if we manage to switch that 30% as well. We assume that there's some small thermal efficiency savings, for example, as you replace old plants with new plants. But basically, we think fuel switching could contribute around a 16% reduction in CO2 emissions in 2050 compared to 2018. So, as I say, it might be possible to go further than that if we can replace that remaining 30% from fossil fuels. And this is where the fuel switching study that what I'm going to talk about today comes in. So back in 2019, we successfully applied for around £250,000 of funding from the Department for Business, Energy and Industrial Strategy, or BEIS, to undertake a desktop feasibility study into fuel switching in cement manufacture. Now, it wasn't just an MPA study, there were some other partners involved in the work. So these were CNR and BDZ, and of course, the funding came from BEIS. So MPA's key role was to project manage the study, and we contributed technical and commercial oversight, provided UK-specific data, interpreted some of the results, and summarised the outcomes and communicated those results to the UK cement manufacturers and the concrete supply chain. CNR were quite important. They developed a unique computational tool, which is known as PKD-MICFD, which I'm sure you all know your acronyms, know exactly what I'm talking about, but just in case you don't, that's Process Knowledge-Driven Mineral Interactive Computational Fluid Dynamics. I'll probably just refer to it as CFD modelling, so that's probably the easiest way to describe it. Basically, it's a tool that can track and monitor the progress of combustion and its location for not only multiple fuels at the same time, but for as many size fractions of any fuel particles as you want, and how they interact with the raw material feed. So in other words, it very cleverly models what happens in a cement plant. And I'm going to show you some of the results it provided for this project in a minute. So VDZ is the German Cement Association. So it's a little bit like MPA, but it has quite a renowned and internationally not acknowledged scientific kind of institution to it. They've got considerable research capabilities and they provide services to cement producers across the world. Now, in this project, VDZ contributed their expertise on the cement process. They undertook things like the literature review and they helped interpret some of the modelling. They also did some of the techno-economic analysis for the project. So the project itself started with a literature review, just looking for any information on fuel switching in the cement industry or use of novel combustion techniques that might be of relevance to this study, and just to look for what sort of things we should be looking at and modelling in the work. Now, next we defined a reference plant. So for this study, we didn't want to choose a specific UK plant to model because we knew there was another phase to the funding that involved the demonstration. And at the start of the feasibility study, we didn't want to commit a single producer to offering up a plant for that demonstration, since they had no idea what they'd be letting themselves in for. So we needed a reference plant that could be modelled that would be as closely applicable to as many UK plants as possible. And I'm going to explain what that reference plant was in a minute. Next, we had to choose an appropriate kind of biomass fuel specification and fuel mix. And that was kind of roughly determined based on what is known today about how fuels interact in the kiln and also their availability, which is quite important. We then proposed a number of scenarios to test before CNR brought in their CFD tool to model those scenarios. And then from that modelling, we put together an optimal fuel mix and assessed the impact it might have on things like clinker quality, techno-economic considerations, etc. And the optimal fuel mix was then used to determine any stages of further investigation, which I'll talk a little bit about at the end. So the reference plant we chose for the modelling was this one, basically. So it's a dry kiln process with a 5-stage preheater. So on the diagram here, you can see these sort of 5 cyclones here. That's the preheated part of the plant. And it had a calciner here with a tertiary air duct, which is this one here. It was a rotary kiln and it has a grate cooler, which is this end here. So it was chosen as a plant with a size or a capacity, of 3,000 tonnes per day of clinker, which equates to around about 1 million tonnes per year. So still on the reference plant, this image shows the geometry of the main burner used. So the kiln is assumed to be 57 metres long with a radius of 3.64 metres. And the burner is a multi-channel burner, which essentially means you can use it to fire different fuels into the kiln. There's lots of technical things it does as well that I don't fully understand, but relating to how the air swirls and things like that to make sure the fuels burn efficiently. I'm not even going to pretend to understand. It's very complicated. And yeah, it helps those fuels burn efficiently and in the way required for clinker production. And this is the calciner. So the residence time, or the length of time the material remains in there, either combusting in the case of the fuel or calcining in the case of the raw meal, is more than 5 seconds. And the tertiary air inlet is this sort of square green patch here. That's quite important. I'll come on to that, to sort of why that's important in a bit. And there's sort of various places you can input the fuel, and there's 2 meal inlet locations, which are down here somewhere, I think. So in terms of fuel selection, the project team used experience of the manufacturing process, along with the knowledge of fuel availability, to propose a fuel mix of 70% biomass, 20% hydrogen and 10% plasma. So plasma energy is a complete unknown for cement manufacture, and therefore presents a more challenging technology. So as a result, it was selected to contribute a smaller fraction of the heat required, particularly in the calciner, and several different options for its use were proposed. Just in case you're unaware, plasma is used in things like waste treatment. So we knew it's possible to use it. It just has never been used in a cement environment, which is obviously quite alkaline, quite dusty. So we don't know how the plasma burners themselves could withstand that. So it was quite an interesting thing to propose. So for the biomass, fuels with different physical properties were chosen for firing at the kiln and for the calciner. And the reason for the difference in physical properties is that calciner is able to accept larger particle sizes or chips that require less processing effort, which in turn makes them a little cheaper and easier to access. The biomass chosen was a 40-30-30 mix of wood, processed sewage pellets and meat and bone meal. So that mix of 40-30-30 was the same for the calciner and the main burner, but the fuel for the main burner was further dried and ground before use. So this diagram shows different scenarios that were modelled. For both the kiln and the calciner, there was a baseline scenario which used 100% coal. And then for the kiln, there was just one scenario, which was a 50% hydrogen, 50% biomass mix. For the calciner, we used a ratio of 83% biomass to 17% plasma, but the unknown quantity of that plasma meant that 3 different options were put forward for how it was used to inject heat into the calciner. And those scenarios are much easier to describe with a diagram, which I've got here. So this diagram on the left here is the coal-fired case. So this is the sort of reference plant at the baseline, 100% coal. In scenario 1, which is this one here, the plasma burners used kind of external to the calciner almost to produce gas by gasifying the biomass, which is then introduced at about 1,000 degrees C. So you can see it just says gas, I think, on each of these inlets. In scenario 2, the biomass is used to replace the coal and the plasma is injected into that tertiary air, which is why I was kind of pointing that out on the reference plants that's up there. And then in scenario 3, the biomass is injected through four burners, but instead of using the plasma to increase the temperature of the tertiary air, you have 4 different plasma torches located close to those biomass injection points. So, and plus an extra one, there was actually 5, an extra one in the riser duct down here. So the CFD modelling looked at a number of properties or characteristics, including things like aerodynamics, burnout of the fuel, the temperatures reached, the oxygen content, carbon dioxide emitted, water, NOx, and bed and clinker formation. I'm not going to present the results on every single one of these, otherwise we might be here all afternoon, but I have picked a few just to show what the modelling does, which I think is quite interesting, but also some of the interesting results that came out, just to give a bit of an overview. So starting with the kiln, this diagram showing the burnout or how well the fuel combusts. So this diagram at the top is the baseline scenario with 100% coal. And now it's worth remembering that these kilns and the calciners are effectively designed around the use of coal. So these show what we're sort of trying to achieve. So in this case, we've got a nice long flame in the centre of the kiln that's not touching the edge in any way. Well, yeah, it's probably hard to see, it's quite small, but it's not touching the edge. This picture below shows the fuel switching scenario. So just as a reminder, we're putting 50% hydrogen and 50% biomass into the kiln here. Now, hydrogen burns very quickly, which creates a short, sharp flame. And that is assisting the ignition of the biomass. But because it has a bigger chip size than coal, which is normally ground kind of micron-sized particles, these larger biomass particle sizes kind of continue burning as they travel down the kiln. And some end up on the surface of the bed where they continue burning. So you can see in this diagram here, this is a cross-section of the end. You can see some of the particles sort of making their way into the bed at the bottom. Going back to that co-processing discussion where I mentioned co-processing and how any ash and fuels is recycled into the spent product, this kind of dropping of the particles onto the bed could impact the clinker quality. However, there are things that can be done to optimise that. And that's one of the things that modelling was sort of helping with it to an extent. But there's things like the burner design and things like that we need to look into a little bit more. These images are now looking at the difference in temperature for the two situations. So the red sections are sort of the higher temperature. And you can see this bottom diagram with the hydrogen, you've got a lot more red sort of at this end of where the flame is, showing that kind of short, sharp hydrogen flame compared to coal, which is kind of goes, the heat spread a bit more, disperse a bit more. You can also tell the flame's a bit shorter because you can see the exit temperature for hydrogen case is lower than for coal. So we've got 1099 degrees C for the hydrogen and 1120 for the coal. Now, oxides of nitrogen or NOx are another interesting one with significantly different results for the hydrogen in the biomass case compared to that of coal. So the use of biomass, which naturally contains significantly more nitrogen than coal, increases the production of NOx. So the blue end of the scale here is the sort of very low NOx production, whereas when we start getting up to the sort of red, yellow end, we're getting a lot more NOx. But as well as the biomass, the higher temperature of the hydrogen generates thermal NOx as well. So we've got this massive increase. So the diagrams are looking really different for this. So that's just a few of the results for the kiln. I'm now just going to go on to look at some of the Calciner results. So this one's looking at the burnout of the fuels, first of all. So this is actually showing the residence time of the fuel in the Calciner. Again, this image on the left is the coal base case. And this one, we've got two on the right, which shows scenario 2 and scenario 3. Scenario 1, which would be here, isn't shown because we're looking at the burnout of the fuel particles. Scenario 1 didn't involve injecting any solid fuel into the calciner because it was just using the plasma energy to gasify the biomass and then inject the gas. So there was no result for scenario 1 in this case. So the fuel switched images look quite different to that of the coal base case. So the coloured trajectories show how long it takes for the particles to leave the calciner. Now, biomass has quite a high residence time, which improves the burnout of the particles. And we found that injecting the plasma near the burners, which was shown in this one, kind of leads to improved combustion. So you can see the lines are a lot more blue, showing a shorter residence time here than they are here. This time, the images are showing the calcination of the raw meal. So the blue end of the scale is showing the start of the calcination, and the red is showing the fully calcined material. This time, all 3 fuel switch scenarios are shown because they've all got the raw materials going into the calciner. In this case, scenario 1, using the biogas, leads to greater calcination. So you can see that there's a lot more red in there than the other scenarios. And scenario 3 had the lowest calcination level. This image shows the temperature within the calciner compared to the coal base case. So the fuel switch scenarios all developed some hotspots within the calciner, which is shown in red. So that it's not so easy to see, but you can see in the coal base case, we don't get any really red. There's a little bit around here. But in scenario 1, we have a bit here. Scenario 2, there's quite a few hotspots. And scenario 3, it's quite red down here, although it is quite awkward to see. That's not necessarily something we want. So we need to do some optimizing to try and reduce those hotspots. So just in terms of a bit of an overview of what those results were showing, we found that existing kilns and calciners can be adapted to operate with zero carbon fuels. So the simulations or the modelling indicate that there's no negative impact on the clinker quality, the kiln stability, or any sort of build-up issues within the kilns. However, some kiln and plasma burner developments are needed to refine things slightly just to make sure we don't sort of unnecessarily wear out refractories and things like that. The flame high temperature in the kiln can be tolerated with some optimization of the burner, both in terms of its design, so how it's injecting that fuel in, but also its location, just to try and maybe fire the particles, at a slightly different angle so they don't quite reach into the bed possibly. Now, the best locations for the plasma burners going into the calciner may be limited by space on site, and things like using multiple burners might cause infrastructural difficulties because of increased power demand. And the choice of plasma gas, so you can use things like ambient air, steam CO2, argon, or hydrogen, that still needs to be determined. And the efficiency and ability to operate that plasma burner in a dusty calciner environment needs further research. So the hotspots in the calciner must be reduced. The location of the plasma injection in relation to the hot raw meal coming in and the biomass inlets needs further investigation to try and improve that heat absorption and make sure the heat's going into the raw meal and not into the side of the calciner. And scenario 2, where the plasma is introduced into the tertiary air, kind of appears from the modelling to offer the best opportunity to kind of quench some of those extreme temperatures and reduce those hotspots. So following that feasibility study, we successfully applied for a further £3.2 million to demonstrate fuel switching at 2 plants. These are physical demonstrations at 2 cement plants. The work has been delayed due to COVID, but the trials are due to take place in the next few weeks, actually, starting in September. And the whole project is due to be completed in March next year. So the demonstration are actually looking at putting biomass and hydrogen in the kiln at Ribblesdale and plasma and biomass in the calciner at the Tunstead Works in Derbyshire. So far, the sort of preparatory work to those physical demonstrations have raised quite a few issues which we weren't necessarily expecting. First of all, we were looking at using 1 megawatt plasma torches. They are really difficult to source and they're extremely expensive. They tend to be much smaller powered units. So what we're having to do for the demonstration is use a much smaller torch. And because it's not going to be inputting the kind of heat demand that we were sort of hoping for, we're really using it now to investigate the ability of the torch to work in that kind of calciner environment, if it can withstand the sort of dusty conditions without the kind of anodes and the cathodes deteriorating so quickly we have to continually replace it. Secondly, we found that a small trial of only a few days would have consumed more than the entire UK supply of hydrogen, which was a bit of a shock. Well, it was a shock to me anyway, because hydrogen's talked about a lot, and this was just a tiny trial for a few days at one cement plant. So just to kind of find out that the hydrogen just wasn't really there was a bit of a surprise. So we had to scale that back too, but we should still get some very useful results from that part of the trial. Finally, biomass availability is also a potential problem. So for the trial, we had to source some alternatives to the wood sewage pellet meat and bone meal optimum mix that was identified in the feasibility study. Now, the part of the problem we have with biomass in the sector is that there are government incentives which provide support for other consumers to use the biomass. And cement manufacturers don't qualify for that support and therefore kind of struggle to access that market. And it's something we've been lobbying for quite some time to be able to access some of those incentives and be able to compete with other users. So although we're still to undertake those physical demonstrations, we're already aware of several enablers that will be required before fuel switching to this kind of biomass, hydrogen, plasma or electrification will become a commercial reality. The sector needs support to access waste biomass fuels, and it needs to be equivalent to that received by other consumers. The production of hydrogen via low or zero carbon means is required at a cost that won't affect the competitiveness of the sector and in quantities that make its use viable. So there's still some way to go, but these studies have been some really important first steps. We know that there's more government funding for fuel switching becoming available, and it'd be great if we can kind of overcome some of these hurdles and barriers identified in this work. So I hope that's been an interesting overview, and I'm happy to try and answer any questions.
I'll start off with one then. I must admit I was quite interested in 2 points. I was wondering where the hydrogen was expected to be coming from. That was the first point. And perhaps you could tell us how, where that's sourced and how that comes about. And on the biomass side, you talked about the shortage of biomass. In terms of biomass, are you talking about RDF? Because can that be used in any way in the kilns? Because we export literally millions of tons of that to Europe, which seems crazy when we can use it on our own shores rather than sending it overseas and again increasing its carbon footprint by having to transport it. Just start those as a kick-off, if you like.
Yeah, no, thanks, Steve. So the hydrogen at the moment is coming from non-low or zero carbon options because it's just not produced at the moment in the UK. So I always forget the colour scheme. I think it's grey, and then blue is a different one and green is a different one. So I think it's the grey one. But I think we had to go with what was available, and it's a good test of whether we can actually use the hydrogen in the kiln. The government are doing quite a lot at the moment in looking at how to set up business models to make sure we have the hydrogen production, either the steam methane reformation one with CCUS, so carbon capture, or using electrolysis, so using electricity to make, or renewable electricity to produce the hydrogen. And in terms of, I don't know if this is part of your question, but just because it might be interesting, transporting it is another issue. So we're having to tanker it all onto sites, which comes with a few kind of logistical issues as well. And then again, another thing the government are looking at is how you could use pipelines either to add the hydrogen into the natural gas grid, or having possibly separate hydrogen pipelines. There's various interesting projects going on around the country. Actually, I think Kiln University has a separate kind of gas network that's off the main grid. So they've been trialling hydrogen But there's kind of a little bit more to it than just putting it into the pipelines, because various appliances, not just industrial plants, but things like your cooker at home, for example, or your boiler, they need to be able to accept the hydrogen as well. So there's sort of hydrogen being looked at in sort of various ways. But yeah, for this project, it wasn't zero carbon hydrogen, but the plan would be that if the sector was to move to hydrogen, we'd be looking at using the renewable sort of hydrogen. On the biomass question, yes, so refuse-derived fuel, the sector is already using. So refuse-derived fuel is great. Of course, it's only a part biomass fuel, so it's roughly the kind of RDF that the cement sector sources tends to be about 50% biomass and 50% sort of fossil waste. So we're already using about 27%, or 27% of the thermal input is from RDF. And another interesting thing might be how we could use hydrogen with something like RDF, which is more available, to fire more of it. So there are limits to what a cement plant can take in terms of biomass. We couldn't just go to sort of 100% biomass, because it just contains a bit too much moisture and things like chlorine and sort of other things that can cause blockages and stuff like that. So so RDF is used now. I think Cemex they had a few press releases earlier in the year. So they're looking at using a bit of hydrogen with higher proportions of things like RDF, and that would be, they'd use the hydrogen to help fire that RDF, which would be, it's quite an interesting thing as well that they're looking at.
Thank you. Do we have any other questions?
Yeah, could I ask one, please, Steve, of Diana? You mentioned one of your early slides was referred to an increase of 4 kilowatts per tonne of clinker, I think. And you talked later on about electrification. Obviously, kilns are a huge energy consumer. How confident are you, how confident is the MPA and its members as to the future supply of electricity, as we're all moving to either buy or think about buying cars, and everything else is going on at headlong pace to meet government targets? It's quite a significant change ahead. How confident are we that there will be sufficient energy?
So I think this I hope I'm not slightly sidestepping the question here, but the Climate Change Committee recognised in their 6th carbon budget that for all the electrification that's kind of expected to be needed to decarbonise exactly that, vehicles as well as industry and household heating, etc., the grid would probably need to double in size at least by 2050 compared to its current size, which is a really significant change. Are we confident? I think yes, but it would come at a price, and that's worrying for our sector, because UK industrial electricity prices are already some of the highest in the world, and that puts us at a competitive disadvantage. So if we've got to go through this whole expansion thing and it disproportionately falls on energy intensive industries, then that is a worry. And one of the points in the roadmap is that we need government support to be able to deal with that. So if you're going to do it, that's great, but we need the support. Now, one of the other things, which is going slightly off topic here, but the roadmap looks at some of the downstream benefits of concrete in use. And one of those benefits is thermal mass, which would help reduce the need for heating and, more importantly, cooling, because we're seeing hotter summers. More and more people are probably going to look to put their air conditioning in houses. And so we're sort of pointing out that actually concrete could be used to help reduce that need. And so we kind of, like, the materials we're all producing then have benefits for reducing that need for electricity, which will be of benefit later. Even if you're producing zero carbon electricity, if you can reduce the amount of that you need to consume, it's still of benefit in 2050. So I think we've got to be really careful that we don't just go, oh, we're producing all this electricity and it's zero carbon because it's sort of solar and wind power. Therefore, we can just use as much of it as we like. We've still got to be really as efficient as we can be with electricity. So, yeah.
I think we're already ahead of you on that one, because our Somerset Earth Science Centre has got massive concrete blocks in the back wall of it for that reason.
Oh, brilliant. That's good to hear.
Any other questions?
Yeah, one from me, please. There's just an interest of, although it's on a much smaller scale, would this technology be kind of quite easily trialled in asphalt plant dryers and burners? Appreciate it on a much smaller scale and probably have less emissions, but we've got a lot more of them and the technology is probably a bit smaller, and just wondering if it's scalable and if that's something that's been investigated.
So we haven't linked it to the project, but one of the things we're sort of looking at is whether this next phase of funding, there might be an opportunity to trial exactly that. So MPA has a sort of another fuel switching project, which is looking at the lime sector. And I think, in my head, we've got cement, lime, and asphalt's the next biggest energy consumer, I would say, within MPA. So, whether there is an option, particularly those asphalt plants that are on natural gas, could they just be switched over? There would definitely need to be some sort of research to make sure that the plant can take it, and because the flame is different with hydrogen and with natural gas. But I think that's definitely something that should be considered, and maybe MPA should look at the next phase of funding how we could do something for asphalt. So I think it'd be quite interesting. Yeah.
Okay, thanks.
I have a question. How much benchmarking did you do on an international basis, and where are the other cement plants? Because of course they're all run by multinationals, and where are they at in terms of alternative fuel? And what's the state of the rest of the industry at worldwide in terms of alternative fuel research?
So we know that the plasma part of this was a world first. We don't think anybody else has sort of tried that part of it. I think hydrogen has possibly had a little bit more interest, and as I mentioned, Cemex are looking at using it in their kilns now. But in terms of fuel switching, I think Europe as a whole is quite far ahead of many other parts of the world. I think the UK sort of 47% replacement is very close to the European average, which I think actually might be slightly lower, around sort of 45, but it's very close. It's So we know that there's also been a bit of research looking at microwaves, which is another sort of electrification or way of using electricity to do the kiln. But yeah, in terms of actually demonstrating some of this thing, we think we are a bit ahead of others, just from that literature review that was done as part of this project. There's other things going on, though, within the sector. So in Europe, I don't know if you've heard of, there's a project called LILAC, which is low emissions intensity lime and cement. And that's quite interesting because that's using a very different, to be honest, kiln system, where you sort of separate the fuels and the raw materials. And the idea behind it is that you can then capture the very pure CO2 that comes off the raw materials, the process emissions. But by having them separate, you can kind of increase your options for different fuels. And you could use a lot more of the RDF, for example, or electricity becomes could be used as well. So yeah, there's sort of different projects going on that are sort of linked, even though they might be coming more from the sort of carbon capture angle. They're still sort of, from a fuel point of view, it's still quite interesting as well.
Okay, well, if there's no more questions, I'm not sure that I can sum that up, but because you certainly gave us a wealth of information there, and I'm sure when hopefully your PowerPoint will go on the Institute of Quarrying links that we put round after these meetings, so people can delve into the information a lot deeper. There was certainly some big figures there and some big targets to aim at. I think it'd be interesting to see how long it actually takes to get into reality from the sort of pilot projects, because that's the important thing. It's not just about doing the pilots, it's about delivering it as a real thing. And there's certainly some challenges in terms of what you're saying with getting hold of sufficient hydrogen and other issues. Certainly from the quarrying aspect, it's a huge step forward. Obviously in our industry we try and sort of do things like using energy efficient motors and managing our fuel economy and using recycled aggregates where possible. And I think we've got a long way to go in our industry in terms of trying to reduce our carbon footprint as well. I think the good news is if you can produce lower carbon cement, people will be happier to use it instead of trying to find other ways around it. And as you mentioned, the cooling properties of concrete to reduce our summer heating would be good, and that would all mean more demand for aggregates if they're using concrete. So I think that could be a win-win for us. So I'd just like to close the meeting and say thank you very much, Diana, for a fascinating talk. I think a lot of it might have gone a bit over the top of our heads, but I'm sure we can look into it, and it's given us an insight into another world that is very aligned to ours and very important. Thank you very much. We can show our appreciation in the usual way, but it's probably a bit of a quiet clap. So thank you very much, and we look forward to seeing you again.
That's great. Thank you.